Going into ECG, we can go right into the software itself. This trace is from a mouse. We are getting lead 1, lead 2. The software is deriving lead 3 and calculating AVR, AVL, and AVF. We are sampling at 1,000 samples per second, and we have 5 seconds across this display time right here. Now, the key to success with ECG recordings is going to be your signal to noise ratio. So the cleaner you can get that signal, the better, and the easier for analysis in general. Again, that's sometimes trickier said than done. Which is why it's important to be able to analyze sections of data. With the advanced ECG analysis module, these are available for offline calculations, so after the fact. So if we click on that offline calculation, we can see again in this top panel, we're seeing our ECG trace. So that's from lead 1 currently, or we could look at it from lead 2 if that's our interest. So any of the channels that are in that main screen, we're able to actually do a full analysis on if we're interested in that. So let's go back to lead 1 just to show you how this works. We're going to put our cursors on each side. Now, for our data range, again, if we're just interested in the selection of data, then we can just look at the selection of data. But more often than not, the researcher is looking at typically either the block of data, so the current block would be from the start of recording to when you stopped recording. So generally that's one animal. Or you can do a complete file. Some researchers will do one data file per animal, so they can see well, they save their data that way with. But for this one, let's take a look at the current block of data. So that's from the start of recording to the end of recording. So we'll go to settings, and with settings, we get this button here that load presets. Load presets is going to go through different presets for different animal models: human, mouse, rat, rabbit, zebrafish. So in our case, we're working with a mouse. When we click OK, what that's going to do is set our typical QRS width, so it's going to set these numbers to what a typical mouse is. And again, that's not a hard, fast rule. Any of these factors can be changed. But it puts it somewhere in the ballpark of what the typical mouse is for that. Now, for averaging, say that we're looking for arrhythmias. So the software is very good at picking up arrhythmias, but we would average every 1 cycle. We wouldn't want an average if we're looking at arrhythmias, because we'd want to look at each beat to see if, okay, how many PVCs or preventricular contractions are going on with this. For this particular mouse, so some researchers use it for just taking a look at either drug models or knockouts. So we can average, and especially if you have noisier data. This is fairly clean data. If you had noisy data, you could average several cycles, or you can average a time frame, and that will help clean up the signal. We offer the QTC type. So this will allow for you to pick which QTC, if you use Bazet, Federicia, Framingham, or the Hodge model. We allow you to establish where you want to measure ST elevation. So if that's important, and again, if you don't agree with where the software is finding the ST elevation or where it's calculating, you can manipulate that. The isoelectric line, again, this can be set in one of 3 ways. We could use the mean of all points of the data. On the vice versa side, we can pick a set 0 line and determine that that is our isoelectric line. Or generally, what I like to do is looking at the mean of the pre-points. So the mean of the pre-P points right here is going to be that baseline right before that P wave, and that's going to be individual to each beat. We want to let the software know if the P wave may be larger than the R wave. So if that P wave, for any reason, for inflammation or for any reason that P wave is larger, then we want to let the software, so that way the software is not seeing the P wave as an additional R wave. Same is true with inverted T waves. So there are some drugs, for example, that will invert that T wave. You can let the software know. Now, ignore the first time in a block period. So sometimes there's setup time. Say takes 20 or 30 seconds for that for you to get settled in, for click that record button, and then you're fiddling around with the mouse, making sure that the leads are in the right spot. So that will that's where you can actually take time in that block and ignore or not ignore. And again, we have our cycle detection threshold sensitivity. So that's going to determine how sensitive we want that animal. So again, here's our values right here. And the lines up here are showing that each one of those beats was calculated by the software. So that shows that our cycle detection sensitivity is accurate because we're actually getting each beat. Now, with each group, we are averaging every 10 cycles. So on our graph here, we're showing all of our data. So let's go to one further down after it's been running a little bit. So say group 28. So group 28, again, consists of 10 different beats, 10 different cycles. Now, if you notice, there's a lot more cycles in this right here than those 10 that are checked. Those other cycles did not meet this detection algorithm. And again, we can control that. So, but our cycle duration right here, take note, our cycle duration seems a little bit off. We have our P wave, we have a QRS, and we have a T wave, but then we could see the next P wave. So what we want to do is take that and shorten it. So we'll hit recalculate. And then we're able to actually see, we could still stretch that a little bit. So that way we can get a better look at just the one cycle. So again, let's go back to these groups. So each one of these groups, we can go through any in the group and see the individual, the black line in that group, that black trace is that ECG cycle in that. So that's that 1, 2, 3, 4, 5. So each one of those is shown and represented here. That green line is showing what was considered that isoelectric line that we said that mean of the pre-P points. The red line that's in here is the average of those 10 in this group. So this group of 10, that red line is showing your average. And we can show that just a little bit easier by showing the average. So again, we can pull down this menu and view average ECG graph, and that will show the average. So this again brings up that detection. So as I was saying, there's a lot of cycles in this group that didn't meet the qualifications to actually be counted by the software. We can actually see those here. We call those outliers. So if we go, for example, B 1149, we can actually find that and see that it's not checked off. 1149, and it is right here, and it is not checked off. So it's considered an outlier with it. So again, it's considered an outlier. When we click on it, let's take a look at our ECG graph. When we click on that 1149, we can actually see where it falls. And something about that one trace, the software didn't deem actually fit with the parameters for our measurement. So how can we change that? What if we don't agree? We could go to our detection algorithms right here. So our detection algorithms will actually go through and say, you know, I don't think the software quite showed what I wanted it to. And the easiest way to do that is, again, to look at the ECG graph. This will show us, again, where that software determined the beginning of P wave. You don't have to agree with where the software determined the beginning of a P wave. You can move that and move the line. So as you move that line, notice that down here, our calculations will change as well. So we're in group 13. Whatever line we move here, we can move the end of the P wave to where we feel it's more accurate for the end of the P wave. Each time we move this, for example, our P duration is changing each time we move it. So that does affect the different calculations that are down here on the bottom. I'll come back to those in just a moment. So again, we can tell the software, we don't have to, the software doesn't dictate to us where the Q wave is or where any of the parameters start or finish. We're able to determine that how we want to determine that. So oftentimes researchers will go through each and they will set the beginning and the ends. And then we could tell the software, you know, I'm doing this quite a bit and it seems to be a trend. I think that you're doing the end of the P wave too late. So you could tell it to get the end of the P wave when that value's at this amount. So that way it will make it better for the rest of the ones. So once we calculate, we're going to remember the manually selected cycles. And then again, now when we go through, we have fewer artifacts because we've changed what our parameters are for our detection algorithms. So again, we can do the same for the end of our T wave. Any of those factors we can change and actually reset those parameters, and that will determine what's artifact and what's not. Now, let's go through the bottom, and then I'll come back up and look at artifact and how this is actually used for arrhythmias. So as with the blood pressure module, again, we can determine if any of the sections are selected. So again, these are groups. Each group, remember, consists of 10 ECGs. So for example, group 9, I don't agree with where beginning of P wave is. So let's take a look at group 9 and do a more deeper analysis. We can move that beginning of P wave. We can move that end. We can move where we determine Q wave, the end of T. There we go. So now when we go down here and look at column number 9, it will tell us our time. It will tell us our heart rate, R to R intervals. Again, all the algorithms are right within the software. So this will tell you exactly, being very transparent as to what the algorithms for the different calculations and how the software is determining it. So again, the table options button is here. So that table options button will allow you to determine what's important for your particular study. This might be overwhelming for you. You might not need all the different numbers that are on here with and all the different calculations. This will allow you to pick which ones are important for you. Say PR, say ST. So you're able to go through, or the researcher is able to go through and pick out what parameters are important to them. So again, it will tell you all the way through. We have, in this case, we have 52 different groups here. It will tell you the mean for the heart rate, for example, what the standard deviation, what the maximum, and what the minimum for each of these values is. So again, all these parameters are here for you. Now, let's go back. One of the big things, one of the big research categories right now, again, is arrhythmias. So for arrhythmias, what we're going to do, as I was saying before, we're going to take one cycle average. We're going to remember the manually selected styles. So again, this will now, we went through our full data set and we did one cycle. So we're showing every beat, every ECG in this group from the start of recording to the end of recording. So there are 521 beats. When we go to the bottom, again, there are 521 beats that you can actually see the mean, the standard deviation, the max, and the minimum for. Again, you can copy this graph, put it into an Excel if you want, or onto a paper. Or you can export it if you wanted to export it that way. You can save the template so that way that graph or that table shows up how you want it for next time as well. So let's look at artifact removal. Again, what we're looking to do at this point, let's take a look. We would go through, the researcher at this point would go through and fix whatever data that they have with that. But this will allow us to set for what we determine artifacts. So in this case, if the rate is below 100 or above 1,000, the software is going to consider that an artifact, and it's going to actually put it in this outliers column here. Again, the same true for our amplitude, for activity, for noise. So you're able to determine and tell the system what you want for the parameters. And it tells you right here what the current ones are. And again, the algorithms are right here. We want to make sure it's very clear how each one of these things is being determined. We also put this in a plot format. So you're able to see in a plot format, for example, this is our amplitude versus rate. And as you could see, we have 3 distinct groups. I moved this box. Currently, it was considering everything outside of this box as an artifact. So it's considering that an outlier. We can correct that with the software. So we can say calculate. We're going to remember the manually selected. So we can set that calculate with, and now again, all those 3 sections of boxes are now within that one box. So we have that 3 distinct groups of data that are breaking themselves up based on rate. And this is how our researchers are isolating different arrhythmias. So different arrhythmias generally have different trademarks that way. For example, you have some that have higher rates. You have PVCs that will have a different R amplitude or will have a difference in that QRS width. So if a researcher is looking for a specific type of arrhythmia, they can box, say that this is that arrhythmia that they're looking at. They can calculate, remember those manually selected, and now their arrhythmias are right here. So this would allow them now to go within their ECG graph. We can go to the average graph, and it will actually show them the data with their particular arrhythmia that they're looking for, as well as the calculations, so they can get a number. So there was 162 beats that met that particular that parameter for an arrhythmia for it. And again, I do highly encourage, the software can do it for you, but I also highly encourage that you look at each of the beats and actually determine where the appropriate beginning end, because software is software, but nothing actually beats the actual expert eye taking a look at that. So that's how this is also used for arrhythmias. And we've tried to make that easy for the researcher to take out different and to show different arrhythmias. For example, AFib or PVCs or bigeminy.